Alright, let's talk about what happens to the length of an object when it starts moving pretty fast. So I've got a rod here, its length L, it's moving super fast in this direction. As soon as the front, there's two frames of reference, A, who's just standing here, and B, who's standing on top of the rod. When the front of the rod gets to A, light shoots up, hits the mirror, and starts to come back down. Now while that light is going up and coming down, B continues to move. And I want it such that when the light returns back to here, the back end of the rod is here. I want this whole rod now to be in this spot right here. So what does the observer at AC? Well, I just said it. Yes. He sees the starting situation. Yes. Light goes up. This is A. Yes. And then when the light gets back down, when light reaches here, we're now at point 2 has reached, the back end has reached point A. I want it to be perfectly timed. So how long is the rod here? Now the rod is moving. A is watching, looking at this rod. It's moving. So distance is velocity times time. And he sees the length of this moving rod. He sees it as V times his time, which is stationary because he's not moving. Again, he's looking at the length of the moving rod as measured using his stationary time. Now, what does the observer at B see the light do? Remember, B is standing on top of the rod. He's moving with the rod. He sees the light leave the front of his rod and arrive down at the back of the rod as he goes underneath this mirror. So he sees the light go up over his head, hit, and bounce and hit the back side of his point number. I think I called this 1 and 2. So it leaves 1, hits the mirror, and comes back and hits 2. So what is B measuring here? B is measuring same thing. Distance is velocity times time. He is at rest with this rod, so he would see it as V times Tm because he's got a moving time. And I'll just want to write down, this is from, what I had up above was the length of this thing moving is equal to the velocity t times stationary. So this is what A is seeing, and this is what B is seeing from those two frames of reference. We do know that Ts equals Tm times the square root of 1 minus b squared over c squared. So I get, if I rewrite this guy, I'm going to put a sense here. Lm moving is v times t stationary. Therefore Lm is going to be v times Tm 1 minus v squared over c squared. Scroll here. But v times Tm is the rest length. Yeah, so I'm just going to try and box this. I got kind of jammed up here, sorry everybody. So the length that someone would see if I was watching a spaceship fly by me really fast, its length that I would measure would be the length of the thing if it wasn't moving times this factor. Now keep in mind that this factor is always less than 1, always. So therefore, something times something smaller than 1 is always going to be smaller. So lengths contract when things start to move very fast. We'll try sample question. A little tricky. So I've got an astronaut traveling at 0.96 c as she travels from Earth to the nearest star system, Alpha Centauri, which is 4.3 light years away. And light years is a distance, and it's 3.4 light years away if somebody who is measuring from Earth. How far apart are Earth and Alpha Centauri as measured by the astronaut? Now this first little part's a little tricky. The Earth-bound observer is measuring the proper distance, or let's call it L rest, yeah, between the Earth and Alpha Centauri. It's the astronaut that's observing the length being contracted, since the Earth and Alpha Centauri move relative to her ship. So what she sees is her ship, yes, and Earth, right? And she stays still, and Earth starts moving this way, and Alpha Centauri starts moving towards her. So she is observing these things moving. She's standing still, and this length right here is going to get smaller. The person on Earth measures this length as 4.3. She's going to measure this length differently because this length to her is moving. So, I'm going to change colors. The velocity is 0.96 c. The rest, yes, is 4.3 light years. And I'm looking for that, the moving one, yes? I use my formula. Some people might be, whoa, wait a second, shouldn't we be measuring this in meters? Distance is distance. These things have the same unit. This thing has no units. So as long as these things have the same units, I am okay. This is 1 minus 0.96 squared c squared over c squared. Now those c's are going to cancel out here, and I'm going to get 4.3 times the square root of 1 minus 0.96 squared, and I'm going to get 1.2 light years. So she actually sees this thing as shorter than it is, which is good, because if she didn't see it as shorter, it'd be kind of hard, because it would light takes 4.3 years to get there. So she's not traveling at the speed of light, and so she's got to be looking at something that's shorter than 4.3 million light years.